This is the opening lecture on what is called Galilean Relativity. Galilean Relativity is concerned with the following. It's concerned with describing the motion of an object with respect to two different reference frames, two different observers. A reference frame can be thought of as a coordinate system. By definition, one of those coordinate systems or reference frames is thought to be at rest, and the second reference frame is moving with respect to the first. Whether it be Galilean, special, or general relativity, what relativity is concerned with is describing the motion of an object with respect to those two different reference frames. Okay, let me begin to write out this description for you. Galilean relativity is concerned with describing the motion of an object with respect to two different reference frames. By definition, one of those reference frames is considered to be at rest. And the second reference frame is moving with respect to the first. Now, in relativity, you're going to hear me say the following phrases a lot: with respect to or relative to. Those two phrases mean the same thing. When it comes to writing the phrase with respect to on the board, I do abbreviate it a little bit. I write it as WRT. So when you see me write WRT, it means with respect to. Okay, Galilean relativity begins with a number of definitions. The first is defining the reference frames themselves. As I mentioned, one of the reference frames is considered by definition to be at rest. That reference frame is called the stationary reference frame, and we refer to it as O. The letter O stands for observer. Okay, so definitions. We have first of all O. O is the stationary reference frame. Okay, and then we have the moving reference frame. The moving reference frame is referred to as O prime. Okay, now before I go any further with this topic of Galilean relativity, let me describe to you how it is that we're going to tackle this topic. We're only going to tackle Galilean relativity for the easiest possible cases. We're only going to consider 1 and 2-dimensional cases, not 3-dimensional cases, and we're only going to consider velocities that are constant, no accelerations. So we'll only consider 1 and 2-dimensional cases with constant velocities. So no accelerations. So we're simplifying. So then therefore, with that in mind, let me continue now with my definitions. We now define the motion of the moving reference frame O prime with respect to the stationary reference frame O. That motion, however, is at a constant velocity. That constant velocity vector is referred to as u. So u is the velocity of O prime with respect to O. Okay, and now let me begin to diagram out exactly how we connect the two pictures, if you will, the stationary reference frame and the moving reference frame, to the motion of an object. What I'm going to do is I'm going to draw it all out for you, first of all, here on the lower board. After I complete that drawing, then I'm going to demonstrate it for you, but I'm going to have to show you another video in order to do so. So let me first of all diagram it out here on the board. Okay, in the demonstration that I'll perform in just a few minutes, we're going to consider yourselves as if you were sitting here physically in my classroom as the stationary reference frame, sitting here stationary at the desks. And then even though you can't see it at the moment, I'll show it to you in the demonstration video, I'm going to consider the origin to be the door over there to my right-hand side. So let's consider then you guys as the stationary reference frame O, and then right here is the origin associated with your reference frame. We just consider that to be the door here in the classroom. Okay, and then we have the moving reference frame. The moving reference frame is going to be me. We're going to consider myself to be O prime. And then when we start the clock at times t is equal to 0, when my demonstration in just a few moments, I'm going to be standing initially at the door. So right here is the O prime reference frame, that's me, and we're starting the clock at times t is equal to 0, and I'm standing here at your origin. I'm standing at the door. Okay, and then some time t goes by, like so. And at time t, because I am in motion with respect to you, I'm going to have a position relative to you here in the classroom. Once again, you'll see this in just a few minutes in the demonstration video. But after some time t goes by, I'm right here, like so, whereas your origin is still over here at the door. Okay, and then we have an object somewhere in this classroom. Typically, when I demonstrate this topic, if you were all physically sitting here in my classroom, I would ask for a volunteer to serve as the object. That would be a student who is walking through the room. And then what Galilean Relativity seeks to do is describe the motion of that student with respect, first of all, to you guys, the stationary reference frame, and then secondly, to me, the moving reference frame. What we want to do is mathematically link the two pictures together. So then therefore at time t, we then have the object, another person, somewhere here in the room, like so. Okay, and now on the board, we then describe the position vectors associated with this object. For example, relative to you guys, the stationary reference frame, and once again your origin is the door, you would see the object, this student, with a position vector. That position vector looks like this. This position vector is referred to as R, and yes, it is another definition. Let me go ahead and write it down. Okay, so R is the position of the object with respect to you guys, the stationary reference frame, O. However, notice on this diagram that I would see the position of the student, the object, differently. I would see the position as this vector right here. This vector right here is referred to as R prime. It's once again a definition. In this case, R prime is the position of the object with respect to the moving observer, O prime. Of the object with respect to O prime, the moving observer. And then lastly on this diagram, and then therefore completing a vector triangle, is the position of me, O prime, relative to you guys, relative to O. That's this vector right here. Like so. This vector right here is equal to my constant velocity relative to you guys, u, multiplied by the time t. Think of it very simply as distance equals speed times time. And now, using the tail-to-tip method of vector addition, I can now relate the vectors on this triangle together. Notice, for example, using the tail-to-tip method, that ut plus r prime is equal to r. We usually write the expression, however, like this. r equals r prime plus ut. This expression right here is the first of what is referred to as the Galilean transformation. With the first of the Galilean transformation, what we've done here is we've described the position of the object relative to the two different observers. How we each see the position of the object, however, depends upon our position relative to each other. Okay, now what I want you to do at this point is pause this lecture, and then pause the lecture and then take a look at the demonstration video that shows the demonstration specifically of this triangle. Go ahead and look at that demonstration now. Okay, now that you've looked at that demonstration and you can relate it here to this triangle, let me now describe what is referred to as the velocity transformation. The velocity transformation is a description of the velocity of the object with respect to the two different observers. Here's then how we find what is called the velocity transformation. What we do is we take the position transformation equation here and we differentiate it, that is, take a derivative with respect to time. Recall that velocity is the derivative of position with respect to time. So for example, if we have right here the position of the object relative to the stationary observer O, by taking a derivative of that position, we then end up with a description of the velocity of the object relative to the observer O. That's referred to as V. It's, once again, another definition, so let me go ahead and write it down for you. V is the velocity of the object with respect to the stationary observer O. Okay, and then on the right-hand side of the position transformation expression, we now just keep taking derivatives. So then therefore right here we have R prime, the position of the object with respect to O prime, the moving observer, differentiate it with respect to time, and you end up with another velocity. This is referred to as V prime. V prime is another one of our definitions. Let me go ahead and write it down. V prime is the velocity of the object with respect to the moving observer, O prime. And then lastly is the derivative of this expression here with respect to time. Recall that this expression here is the position of me, O prime, relative to you, O, here on this diagram. If we differentiate this, however, with respect to time, we just end up with the velocity u, which we've already described and we've defined earlier. Recall that the velocity u is the velocity of O prime with respect to O. This expression here and this expression here are collectively referred to as the Galilean transformation. Describes the position and velocity of an object relative to two different observers. Now, as you've followed me through this lecture thus far, as you've watched my demonstration video of the triangle behind me, hopefully you were fairly easily able to follow along here in this lecture. But of course, when I begin writing out these vector expressions on the board and define them as I go, right frankly, you probably really have no idea what it is that I'm talking about. But it turns out that you're actually already intimately familiar with how the Galilean transformation works because you see it around you, for example, in the everyday world. Here's a nice, easy conceptual example to wrap your head around of the velocity transformation. Consider, for example, the following situation. Let's say you're in a car, and the car is going down the freeway at a constant velocity of 60 miles per hour, say to the north. So you're sitting in the car and just going 60 miles per hour relative to the ground in one direction. And then you look at the oncoming traffic. When you look at the oncoming traffic, let's say that a person is sitting in one of those cars and relative to the ground, the person is moving at 60 miles per hour in the opposite direction. Therefore, relative to you inside of the first car, what is the relative speed of the oncoming traffic? Once again, you're going 60 miles per hour in this direction, the oncoming traffic is going 60 miles per hour in this direction. What is the velocity of the oncoming traffic relative to you in the first car? If you're thinking to yourself that the relative speed is 120 miles per hour, you're correct. You actually did V equals V prime plus U. What I'm going to do now is pause this lecture here and turn this easy conceptual example here into the opening problem. So go ahead and stop this lecture, and then in part 2 of the lecture, we'll then go ahead and access the examples.